All right, there's another example. You can try this out, and then you can check on the answer as the solution has been provided. All right, isentropy process. Now, guys, the other day, when you learn about uh, Carnot cycle, from the four processes that you have come across with, right? You can see that actually at the beginning of all the processes too, you have the apa ni, the word reversible, and then followed by whether you have like apa ni, adiabatic expansion ke, or even isotonic expansion and so on. Okay, so actually two of the processes that make up the Carnot cycle, yeah, can be categorized under isentropy process, right? So basically, if you have an entropy for a fixed mass, okay, the entropy can be changed due to the heat transfer and also presence of irreversibilities, right? So that means the entropy and for a fixed mass will not change, right? If that process is internally reversible and it is an adiabatic, right? So again, guys, in order to have an isotropic process, you need to satisfy these two conditions here. Okay? You must either internally reversible and adiabatic, right? Okay, let's have a look from this example. Let's say you are the turbine, okay, steam flowing into turbine and then rotate the blades, connect to the shaft, and then it produce W out. Okay, now because nature of most devices, they are internally reversible and adiabatic, meaning that in this particular turbine, okay, you have an insulation layer that is covering up the turbine in order to prevent any heat exchange between the system and the surrounding, right? So when that happen, and inside this particular control volume, there are no irreversibilities. Thus, you have an isentropic process. So under isentropic process, it is defined as process during which your entropy remains constant. So delta S must be equivalent to 0 or your S1 equivalent to S2. So here, kalau let's say steam entering this turbine, let's say has a value of S1. So basically at the outlet, and normally you are the mixture, you are the mixture of water or steam. So at this mixture, it must share the same entropy value as at the initial state of the steam over here. So the application of these devices, they are not just simply limited towards turbine, and some other devices such as pumps, for example, even nozzles, and even some diffusers, all of them, they are well insulated, and then they are have no irreversibilities present. So when that happen, you are the isotropic process condition occurred in that particular process. Right, guys. I don't want to discuss in detail on this particular example finding. The solution has been provided. This time you are the adiabatic nozzle, right? So we know for adiabatic nozzle, it best work when it is internally reversible. Right? So when you have this condition, that means you are the isentropic. for this particular nozzle device. All right. So to determine maximum exit velocity, okay. So we know nozzle basically outlet apa ni the outlet area is smaller than the inlet. Okay, let's say state 1 and state number 2. Remember, you punya boundary, the real and also imaginary. So you put all the values here. Inlet, you are the saturated vapor. That means you punya X1 is 1 lah. Okay, so you list down H1, S1, and then happens that outlet, we only know the pressure. Okay, so one of the function of diffuser basically is to reduce the pressure at the outlet, right? At the same time, because working under isentropic, S1 equivalent to punya S2. Okay, so from table S6 ni, because you are using steam, you check S2 value with SF and SG at 1200 kilopascal. So actually in between, that means involved with mixture. So kalau mixture, you have to determine average H. Now, to get exit velocity, right, that is the function of this diffuser, basically to increase the velocity at the outlet due to the change in cross-section area of the device itself. So that means from your energy balance for steady flow devices, guys, okay, remember from the long energy equation that you have, you're the Q, W, the mass flow rate for the inlet, outlet, and so on. From there, we know this is non-W punya involvement. There's no W, there's no Q, and so on. So that means what's left is your mass flow rate on both sides, which associated with your enthalpy H and also velocity, right? So let's say this is the final formula that you have. Okay, so remember, you just simply key in the values and then you simplify that and to get what is your punya V2 here. Guys, remember, you need to show this particular conversion factor. I have mentioned this so many times. Missing and this particular conversion factor will not get you a maximum mark. Now, guys, if you can see, your punya V1, right, is not provided. Okay, but normally we know that because inlet and the area is large, okay, so that's one you punya V1 ni actually approaching 0. So that's why V1 from this calculation is equivalent to 0 meter per second. That's what has been indicated from here. Right? Okay, example 6, please try this out. More or less the same as example 5, but this time you nak cari work output against by using the same formula and so on. Okay, this is about the property diagram involving the entropy. Okay, from our early definition of entropy S, okay, our delta S equivalent to delta Q over T for internally reversible. Now, if we were to try to plot a graph of temperature versus entropy diagram, like this one, and then let's say you are a curve that connecting between these two states, right? Area under process curve basically will give you the amount of energy transfer by heat transfer Q, right? So guys, let's say in this example, you have like some sort of a curve, all right? So the appropriate way of finding the area under this process curve is by performing an integration segment by segment, and then you total it up between the initial and final state and to get the total Q transfer throughout the entire process. And of course, this can only be done if you have an internally reversible process, which is presented by this green solid curve over here. Okay. in case of, remember, internally reversible isothermal process, this is from apa ni, reservoir calculation, whether you have source ke ataupun sink, okay. So you can make use of this equation, your T naught become constant. So from there you can simply find the area under process curve that represent the amount of energy transfer during internally reversible. Another important diagram is the H versus S diagram. Okay, H versus S, right? So let's say from state 1 to state 2, again you have like some sort of a curve connecting between those two states. So the important under H versus S diagram, sometimes known as Muller diagram, all right? The difference between state 1 to state 2 for delta H, okay? This delta H ni actually is the measurement for your punya work component, right? Whereas for your delta S on this x-axis, this represent the measurement of irreversibilities. And how severe does the irreversibilities present and within your device? Okay, so if you like, every time if you encounter or you plot H versus S, so you can actually extract the work component using the y-axis of H and also the irreversibilities on the x-axis for this particular delta S. Okay, guys, again, if you recall back from Carnot cycle that we have from chapter 5 the other day. Okay, and we know that for Carnot cycle consists of 4 reversible processes. Okay, so now we plot T versus S. Guys, remember the other day you have like some sort like, I think P versus V you are the some that curve, something like that, and then yeah, like 1, 2, 3, 4, something like that lah. Okay, now this is for P versus V, but if you plot temperature versus entropy, this is how the Carnot cycle that we have the other day, for the heat engine system looks like. Okay, state 1 to state 2, basically this is reversible isothermal expansion. 2 to 3, reversible. Guys, reversible what? 2 to 3? Reversible adiabatic expansion. Okay, so when you have reversible and then you have adiabatic, so that means you are the isentropic between state 2, state 3. 3 to 4, right? You are the reversible isothermal compression. Then to complete back this cycle and to return back the initial back to its initial state, so you are the reversible adiabatic compression back to state number 1. So here what we can say that area under A, 1, 2, and B represent the W out during the expansion of Carnot cycle. Whereas area under A, 4, 3, and B, this represent the work required during the reversible compression. So the difference between W out minus W in basically will give you the W net of the process. Okay, guys, I want you to try this out. prove that this W net out ni can be simply expressed in terms of QH minus QL. I want you to prove this during your free time. Okay, problem 7. This problem ni actually, okay, again, very straightforward, quite interesting. Please try this out during your free time. And then if you have problem, please do not hesitate to consult with me. Now, another 10 minutes. This is regarding on what we call it as the TDS relation of pure substance or any working fluid. Okay, so now what happens is that, let us assume, okay, you have a compressible substance and within this particular closed system, or even you have compressible substance that is flowing into and out of this particular control volume. That means we have open system and also the closed system pertaining this particular example. Now, from our energy balance equation, guys, as usual, starting from energy in minus energy out, okay, equivalent change of energy of the system, right? Now, in the case of, excuse me, closed system, the right side equation here, we simply left with your delta U because we know kinetic potential has been neglected from here. But you still have Q and W, right? Because there's no insulation materials. That means this is non-adiabatic. That means definitely you are going to have Q and also W due to the movement of the piston, whether moving up or moving down, right? So movable boundary work. So when you express that, you are the delta Q internally reversible minus with delta W internally reversible out. Remember, because we have mentioned Q minus W ni equals to delta U. Q represent Q net in. W2 is W net out. Okay, equivalent to delta U. Right, so you have this particular expression. Now, from our derivation of entropy, we have delta Q internally reversible equivalent to T times delta S. All right, and also that you have movable boundary, right? So the other day, guys, when you learn about movable boundary, is integration of P times delta V. In other words, P times V lah, right? So you have this expression here, right? So substitute this both expression into the generalized energy balance. So you are the TDS equivalent delta U plus P times delta V, right? So as you can see, everything is in capital. So that means the unit is in kilojoule. So if you divide per unit mass, remember T is still maintained capital T. Only the delta S, delta U, and also delta V become smaller per unit kilogram. So here, this is what we call as the first TDS equation, or the first Gibbs equation. From there, this is our first relation: TDS equivalent delta U plus P times delta V. Now, this is from closed system. When you have open system or control volume, that means you are the extra heat transfer by mass flow rate. M1 ataupun simply generalized as M dot flowing in and out of system. So you are the H coming together, because H ni actually already take into account the internal energy, from the internal energy from the workflow, right? Plus also with the internal energy consists in that particular flow, right? So here you are the H equals to U plus P times V. We perform, you differentiate all the term inside. That's why ada delta H equivalent delta U plus P times delta V plus V times delta P. All right. So what happens that you replace, yeah, you replace this delta U from the first TDS with this expression over here. Yeah, so when you simplify, you will end up with TDS equivalent delta U plus P times delta V. Yeah, sorry, TDS, excuse me, you will end up with second TDS equation, TDS equivalent DH minus V times delta P. All right. So here, guys, what we can do when you rearrange back on both first and second TDS, right, and you express it in terms of differential form, you have delta S equivalent delta U over T plus P times delta V over T from the first TDS, whereas from the second TDS, you ada delta H over T minus V times delta P over T. All right. Okay, now what happened? Using the first and second TDS, we try to relate with entropy change for incompressible substance. We know for incompressible substance, right, you have liquid and solid. Okay, guys, the other day, remember that when we learn about specific heat for incompressible substance, okay, we can simply express the punya CP ke or CV dia in terms of general C, right? So here what happens that we know if you have delta U, you can simply express that in terms of C times delta T. Okay, so guys, what happened again from this first TDS relation that you have over here, right? So C bracket T ni is to show that this C ni as a function of T, value of C must be dependent on temperature, right? So when we summarize this, you're going to have C average. Remember, C average ln T2 over T1. And of course, unit is in kilojoule per kilogram Kelvin. Okay, so this C average, guys, you will have to determine from the T average lah, from probably table, I think table A2 kot, to get what is your punya C average and so on, right? Now, this is for any type of process. Now, what happens if I have an isentropic? Kalau isentropic, T1 equivalent to T2. So, ln T2 over T2 ke T1 over T1 sama, right? That will result in 0, right? So, when that happen, you punya isentropic process of an incompressible substance is actually an isothermal process because it has no value because of this particular relation here, T1 equivalent to T2. So guys, as you can see, first example, the importance of the first and second TDS that we have derived earlier is to make use these two equations to come out with entropy change for incompressible substance. And so that means, and let's say if I give you water, let's say any type of solid, when I ask you to form or sorry, to find the delta S for incompressible substance, you need to use this particular equation here, right? This is for any type of process. But if let's say it undergo an isentropic, right, there's no way we can find our delta S, and because actually this process also undergo an isothermal process for this entropy change for incompressible substance. Okay, let's have a look on this example, right? I think it's already 1:48. Okay, I think I'll stop here for today. Do you have any question? Any question, guys? Before we end the session. Okay, no, so far. All right. So in that case, I'll stop here for today. We shall continue this lecture for part 2 next week on Wednesday, same time. For Friday, we're going to have tutorial for chapter 6, the second law of thermodynamics. Yep, apa ni? You have question Yep. So for integrated project, can we take icon lab picture as our plan diagram? Okay, you may do so, but make sure you have like complete sketches and also complete list of equipment and devices that you claim that you use inside the modeling to produce your result lah. Okay. Yep. Yep. Who else have asked question? All right. Miss Im also asked me question earlier for integrated project. Should every member in the video? Okay, guys. Integrated project is the apa ni? How do I say? Is the group contribution. All right. So of course, let's say although let's say you are using animation to presenting your work, that means there's no no direct face of yours yang coming out from the video, but at least you in the end ataupun at the beginning of the video presentation, I expect you to show or list down who are the participants or contributors toward in the making of the video, so that I do aware more or less everybody involved in the making of the video presentation, something like that. Anything else? Any other question? Okay, if not, okay, thank you very much, guys. See you during the tutorial this Friday, right? And please don't forget to to fill in on the post satisfying punya ni Okay.